those remote people, they want the stream. So I assume the stream is back at this point, right? Okay, in any case, I restarted it, so let's hope it's there. So okay, back to this diagram. So this is clear. So segmentation is always in front. If I ask you a question, so how come I was running a GDB, I was compiling my C code, I was disassembling it, I had never seen anything about the segmentation whatsoever in my entire life. How does it work? Like, we know part of it. We know that these segment registers are assumed based on the context, right? So I'm like, if you do a move instruction, like the hardware uses the data segment. But still, you never seen a change in addresses, right? You see 1 megabyte address in the register, and really, like, you see that when something is accessed. Actually, I argue you never see what physical address is accessed, right? You'd never really care, because none of the debugging tools will actually show you which physical address is accessed, right? Unless you're operating system developer and you don't really care. But what I was trying to get to, that in many cases, operating system simply sets the base to 0, effectively saying that I don't really care about segmentation whatsoever. It's just, let's use the segment base as 0 and the segment limit as a max address, so the whole 4 gigabytes are accessible, right? Why is that? Just because the paging mechanism is so powerful. Remember, I said that there is like a user accessible bit and a kernel accessible bit. So you can really split this address space into the part which can be accessed. This green part can be accessed by the user. This is where the user accessible bit set. In my page table, I draw this page as green, those entries green. And if you try to access the page for which the user accessible bit is not set, you get a protection violation fault, right? Then you say, okay, why do I need segments? Like, page tables are so powerful that let's set the base to 0, limit to max, and live with it, right? And this is exactly what was done for many, many years. This is how the operating systems are designed today, like Unix, Windows, everything. It was so widely used that Intel engineers said, okay, you don't want segments, we're going to remove them from our CPUs. And they really did. When they moved from 32-bit versions to 64-bit versions of their architecture, they said, on 64 bits, you cannot set a base to nothing but 0. They only allow 2 special segments. One is used segment registers, FS and GS. And any other segment, data segment, stack segment, code segment, all assume that the base is 0. And Intel says, okay, and you cannot say anything else. And these 2 are survived because they were used to implement thread local data structures, right? Each thread has a private segment where it keeps thread local data structures. And they're relative with respect to FS. So for example, a move instruction from that segment will have FS in front of the move instruction, right? In front of the address, right? Okay, cool. That's what happened again. That's what Intel gave us. And now we, like, literally, we don't really have segments on 64-bit machines, right? They are there, but they are handicapped segments. So they just only have base 0, limit, max. There are some good things about it and some bad things. So good things is that Intel doesn't have to provide extensive verification process which checks that the CPU really implement the segments correctly, right? So there is no bug in the CPU. That simplifies their job. The disadvantage is that you cannot provide isolation within the address space, meaning that if you, for example, say, well, I'm running again my web browser, and these 2 pages are running my favorite Quake example, right? And I don't want Quake to be able to access any other pages of the same address space. Page tables doesn't provide you with this functionality. Like, any page with the address space, which is mapped as user accessible, is really accessible. So if you don't trust this code, if it's some malicious code, then it can access anything what contains your secret or anything, right? if we would have segments, we would say, look, by the way, it's so easy. We can patch this thing and like make sure that it runs in its own segment and we'll never access anything else, right? But this functionality is not there today. And that's a problem. That's why we use WASM and say, look, if I don't trust something what runs in my address space, I have to do this software fault isolation trick, which WASM is a standard, de facto standard right now. And that's the only way to, no, not the only, but one practical way to enforce isolation within a single address space. But the hardware doesn't support anything like that. I'm saying that like I said, that they dropped the segments, then, okay, up until 5 years ago, they didn't care about it at all. They thought that they're golden. Then those security attacks became so frequent that they say, okay, we have to probably come up with some other mechanism to give you a way of providing isolation within the address space. And now they are all of these CPUs, Intel ARM, they have certain mechanisms which are somewhat similar to segmentation, which implement this idea of providing isolation within the same address space. Does anyone know a single mechanism? Can anyone name anything? Never heard of anything? So ARM, huh? The question is like, I said that the Intel CPUs drop segmentation. And they were very happy about it. It was like the decision for them to simplify their CPUs. Unfortunately, it was a wrong decision because in a modern world, the attacks are so frequent that the people want to isolate parts of the address space, and page tables do not allow you to do that. So they brought the mechanisms back. So Intel has something what is called memory protection keys. Never heard of it? Extended page tables with virtualized functions, VM-func, not. So that's on Intel. Intel has a bunch. They're bringing a lot. ARM has something what is called memory tagging extensions. Has something what is called authenticated pointers, pointer authentication. Those are all like isolation mechanisms provided by like the last couple of generations of modern CPUs. Anyway, so good. So we got this. Again, if we say, okay, this is your translation pipeline, no matter what you do, you start with segmentation. The whole translation picture goes like this. You start with a logical address. It has two parts. One part decides the entry in the global descriptor table. Another part is an offset. You add the base with an offset, get a linear address. So there is a linear address space, right? So it's kind of like virtual, but it's both linear. Then you split this address into 10, 10, and 12 bits. You go through page tables, and then you decide you get the real physical address, right? So just again, if you open a manual for the Intel CPU, this is how it will look, right? And those two parts is the first segmentation, second is paging, right? Again, I prefer to cover both because you cannot even boot into main on bare metal without setting up the segments because you cannot enable segmentation, because you cannot enable paging. Again, I mentioned that 32-bit machines support at least two page sizes. So in this example, it's 4 kilobytes and 4 megabytes. So we already covered how the translation goes for the 4 kilobyte pages. For 4 megabytes, everything is much simpler, right? Because each entry in the first level of translation really covers the chunk of 4 megabytes, right? Because there are 1,000 entries, right? 1,024. And each is 4 megabytes. So the entire thing will be 4 gigabytes of address space, right? So you only need one level of translation. So really you take this 20 bits of address, you really take 10 bits of address because the other 22 bits are just simply an offset within one 4 megabyte page. And this 10 bits here decide which entry in a page table you choose. And it's a physical, the entry will contain a physical page number of a physical page, like page 0, page 1, or page 2, which contains your virtual page, right? Again, that's nice. Intel has this diagram for you, which is, again, like encodes this drawing. So what happens here is you take 10 bits here, page table directory, take an entry, page table directory entry with PS, page is present, bit is set to 1, you got the physical page number. Again, you only need 18 bits because you are representing 4 megabyte pages. One last thing which I wanted to discuss is translation in 64-bit mode. Idea is kind of similar, right? But your linear addresses are bigger. So up until like, again, maybe 10 years or 7 years ago, Intel was limiting the address to 47 bits. Despite the fact that we say a CPU is 64-bit, the addresses were set, okay, 47 bits. If you have upper bits, Intel never, I forget how it actually works, but it can be an exception, or it can just drop those bits and say, we don't know what to do with them, right? And so again, since now you're translating your address space, physical memory is also, physical addresses are also not 32 bits or 64 bits. You need 52 bits to provide a physical page number. So those entries in the page table cannot fit into 32 bytes, right? Instead, we use 64 bytes here, right? Which means that if the page table itself still 4096 bytes, then you only have 512 entries, right? Because you divide it by 64, not by 32, right? And so to choose any of those entries instead of 10 bits, you now will be using 9 bits, right? Because it's 512. But the general idea is the same. CR3 contains the 40 bits of a physical address of the root of the page table, which is called PML4, right? And they couldn't come up with a better name. And the top 9 bits of the address choose an entry here. The entry itself is 64 bits. It provides 40 bits of a physical page number to choose the next level. The next 10 bits of the address essentially choose the entry in one of the 512 entries in it. This level is called page directory pointer table, because now you have a bunch of page directories, right? So now it's a page table directory enter. But for PML4, they couldn't come up with a decent name. And now there is PML5 as well. Okay, but the next 9 bits essentially choose the entry in among this 512, and so on. Again, physical page number. The next one chooses a page table entry here, and those last 40 bits is actual physical page number of a real page, and this last 12 bits is just an offset within a 4 kilobyte page, right? So similar, just more entries in a tree. Yeah. Well, offset bits are really just an address, an offset within a page. There will be no access control. So all access control checks, like all access control bits, are contained here, right? And the hardware looks at those bits and says, okay, you're trying to execute a code from a page which doesn't have execute bit set. It raises an exception and it goes to the operating system, and it's up to the operating system to react. Maybe you're trying to do an attack and you're trying to jump to the heap to start executing heap, right? Any other questions? Okay, good. So, but again, we're back to this performance argument. So now suddenly, if you're really trying to access those bytes just to read a value from memory, how many additional accesses you have to do in front of it to even perform this load from memory, because you have to resolve physical address into virtual address. 3? Why 3? Your 1 access here, right, to read this entry, that's 1. 1 access here to read those bytes, right? 2, 3 here, and 4 here. Extreme case, if none of these addresses in between are cached in caches of the CPU, each of these accesses can result into 200 cycles delay, right? So it's suddenly 200 by 4, 800 cycles delay. If you reason about it more pragmatically, you can make the following argument. So look, this is only 4096 bytes. So most likely this one is cached in L1, right? Because L1 is 32 kilobytes. So probably this is not really a problem, because this is always cached, right? You say, okay, cool. What about this one? So this is a Google level interview, and you have to make an argument whether how big, how many of those second level pages are there. So you know that there are 512. Each of them is 4 kilobyte, right? So 512 by 4, what is that? 8 megabyte?
2 megabyte.
2 megabyte? Yeah, 2 megabyte. So okay, 2 megabytes of those entries. What are the chances that these all of them are cached? Definitely not in L1. Who knows the sizes for L2? L2s are large. Each core has L2 of 1 megabyte. So there is at least 50% chance that it's cached, right? That's not bad. So, and cached means maybe like 16 cycles of delay. Okay, not a problem. Your Google interview moves on. They ask you how long it will take to execute. And now you're saying, okay, but how many of those? And then you have to evaluate the size. And most likely, and if this is 2 megabytes, then just again, do multiplication, you will figure it out. But these two other entries are most likely not cached. So most likely, even if you're sitting on a very large memory, imagine it's a hash table and every access is pseudo-random, right? You access something here, something there, something here, something there, and each access requires a page table translation. Then these last two can be easily 200 cycles each. That kind of adds a hit. And remember, I mentioned this additional caching mechanism, which is translation array, TLB, translation leukocyte buffer. It also has a limited capacity. So at some point, it has some, like, not a big amount of entries, let's say 512, maybe 1024. And again, you're saying the same argument applies that you can only translate 1024 or how many entries in TLB are frequently accessed translation entries. But then again, you will be hitting those 200 cycles, right? And at this point, what is your solution? If you're like final stage of a Google interview, what's your answer? What do you have to do?
As you said, probably the top 2 levels, we can use the cache, but for the next 2 levels, probably we can come back to the segment.
Come back to the segment, almost there. Like Google says, okay, man, like we wish we could have, but no. But who can pass this interview? We've seen it in this lecture. So one answer, what do you have to do with your address space? Remember, it's called huge tables, huge pages, right? So on 32-bit machines, you say, I will use 4 megabyte pages. On these machines, and I didn't tell it explicitly, but Intel supports 1 gigabyte pages, which essentially eliminate those levels, right? So you say, look, I will configure the address space with a 1 gigabyte page, and then my accesses will not be penalized by this. Okay, I'm done here. So I'm actually very lucky that I finished. And so next time we can start on actually booting into May. Thank you.